Welcome everybody, welcome back to Module 4 of our Quantum Future with the incredible Jack Hidary. Jack.
Peter, great to be here.
So if you're still with us, and I hope you are, you're finding that quantum computing has incredible applications and it is going to transform every aspect of our lives, not in 50 years, 30 years, 20 years, potentially the next decade. And it's just the beginning of powerful technologies that are being demonetized and democratized around the world. And the notion that we're going from something as powerful as quantum computing that is being developed by governments and the top corporations, soon to be on the cloud and available potentially to free to everybody, is extraordinary. So in this module, if I understand correctly, Jack, can you give us an understanding of what are these quantum computers and what are some of the applications? Is that fair enough?
Yeah, absolutely. So let's just recap a bit about how we got here on this journey into the quantum future. We talked about quantum mechanics itself, this very interesting science that emerged in the early 1900s. We talked about superposition, entanglement. We then talked about sensing and communications, quantum sensing, quantum communications, how that brought us into a new regime of being able to do things, both sensing different magnetic fields and other kinds of fields, as well as communicating in new ways and ways that give us unconditional secrecy that our old ways do not, our old methods of communication do not. Then we really got into quantum computing. What is a qubit, the fundamental computing unit, and then how do we array them together? And now in Module 4 here, Peter, let's dive into how do we build these things? What are they made of?
What are they?
Good, all right, are we ready?
Yeah, absolutely, let's do it.
All right, good. So quantum hardware, there are 8 primary ways to build a quantum computer. Now, in fact, there are thousands of potential ways to build them, but the industry, the academics, have really focused on 8 primary ways to build these things. Anything that's a quantum mechanical system, and in the case of a qubit, bit implies 2, so it would have to be a 2-level system. We talked earlier today about how a quantum mechanics system is discretized, that is, it jumps in units, certain discrete units. And so if we have what we call a 2-level system, i.e. a discrete state of 0, and then another discrete state of 1, and the ability to have a superposition of those two, we have a quantum mechanical system. Now, I should mention right now to our viewing audience that you could actually build a quantum computer from a qubit, i.e. something that has level 1, level 2, and level 3 discrete states, but that is a more difficult prospect, and there are some academics looking at that, but the majority of the industry, Peter, is really focused on a 2-level system. And so let's look at some examples. Here on the screen, what we see is a superconducting qubit quantum computer. This happens to be on the right side from IBM and on the left side from MIT Lincoln Labs. Right. So this is both an academic example on the left side and an industry example on the right side. Now, what is this contraption? By the way, on the left side, Peter, what you see in that red barrel that you see hanging down from that trellis, what's inside there very much looks like what's on the right side. Okay?
The coldest place in the universe.
In fact, yes, the coldest place and the hottest place in the universe are both on Earth. Both on Earth. And so the hottest place, of course, is a particle collider, right? Where we accelerate particles and we smash them against each other, and you're talking about trillions of degrees, Kelvin there. But in this case here, in the case of superconducting qubits, we bring down the temperature to 7 millikelvin. Let's understand what that means. It's 7 thousandths of a Celsius unit degree above absolute zero, with absolute zero being minus 273 Celsius or minus 459 Fahrenheit, right? Now, space in general is about 2.73 Kelvin, right? Roughly 2.5 to 4 Kelvin, rough numbers. So this is orders of magnitude colder than space itself.
Incredible.
Right. Now, why do we have to make it so cold in this kind of approach to quantum computing? Because what we know about these superposition states, these entangled states that we've talked about now over a number of modules, they're very fragile, Peter. They're very fragile.
Meaning,
we say that they decohere, meaning that.
Meaning they decohere.
Right. Yeah. And more specifically, as we talked about, when we measure a state, measure a system in the quantum world, we impact that state. We don't leave it unchanged.
Right.
We impact it. And the way that it decoheres is that something from the outside world, a photon, an electron, alpha particles, impinge on that system, thus measuring it, thus it decoheres, i.e. we lost our superposition, we lost our delicate entanglement, and thus we can't compute anymore. So we have to keep this very, very cold to maintain what we call coherence, because the longer we can maintain coherence, and again, coherence is just code word, jargon word for maintaining that superposition state, maintaining that entanglement state. The longer we can do that, the more computing we can do. And so when you look at a contraption like that, all those wires down there, there's two sets of wires coming down. One set of wires is part of what we call the dilution fridge. It's not like a fridge in the kitchen, okay? This is a different kind of fridge, because they're taking it down to, as we said, 7 millikelvin, 7,000ths of a degree above absolute zero, colder than space. Another set of leads are what we call the microwave leads. These are wires that come down and are going to pulse microwave energy into the system, into these two-level systems, pulsing them from 0 to 1, or from 1 to 0. That will be applying the NOT gate that we talked about before. Or they might pulse in a different way and take it from a definite state of 0 to a superposition state. So physically, what's happening in that dilution fridge is the actual processor itself is on the lower right-hand corner of the right side where that little blue sign is. It's a very small 1-inch by 1-inch quantum processor. This whole contraption is meant just to serve that little quantum processor.
Put the input states and then put the gates or operators on there.
Exactly. Initialize the state, right, to a 0 or 1 or some other state, apply the operators, and then finally do a measurement.
Right.
And when we do that measurement, then the operation is over. We call this whole thing a circuit. So instead of calling it a program like we do in classical computing, we call this a circuit. And what you see on the left side at the MIT site is the controlling hardware that controls the quantum computer itself. So in fact, we don't directly interface to a quantum processor. We go through classical hardware in order to pulse it, understand what's happening, and type out our actual Python code. So the Python code gets interpreted first by a classical computer, and then gets put into the quantum computer, not in the form of code the way we do classical computer, but in the form of microwave pulses in the case of superconducting qubits.
How long does that calculation take, if we're going to call it that?
We're talking about seconds to minutes. Yeah.
Is it instantaneous, or is it seconds to minutes between the time you put in the beginning
for one
state?
operator, it's almost instantaneous. Yeah, for a single operator, you hit that button and bingo, it happens. Now, this is the case, Peter, in this particular, what we call realization or physical realization of quantum computing, the case of superconducting qubits. Let's understand that word superconducting. We both know that certain materials are not superconducting. That is, they might be okay conductors at room temperatures, but you bring them down to really, really cold temperatures, and suddenly they become superconducting.
No resistance.
No resistance to electrons passing through. Brian Josephson won the Nobel Prize in 1984 for understanding that if I take two superconducting wires and put them close together but leave a gap, that we now call the Josephson junction, we can actually turn that into a qubit. That is, we can put that contraption into a state of 0 or a state of 1 or a superposition of states. In fact, we can also entangle two of them together.
Amazing.
So that's what's in the innards of this particular kind of approach to quantum computing. Let's look at another view of the same kind of approach. And now here we see what we call the chandelier. This is a picture now of a quantum computer of the superconducting type.
This is what we saw from IBM.
That's right. And so here where we see the actual processor is in that cylinder at the very bottom. That's where the coldest part of this is. And you can see on the left side here, we have a very balmy, very warm 4K, 4 Kelvin on the top, going down to 1K, and then finally going down to, it says here 20 millikelvin, but in fact now we actually bring it down to 7 millikelvin.
Is the reason it's chandeliered and tiered that way for thermal isolation? What is it that
ultimately we want to isolate that bottom part and really get it down to the lowest temperature possible so that we can maintain the coherence and also get it to the superconducting temperatures that we need to run this kind of junction. So that's one approach to building a quantum computer. Let's now turn to a different approach, a trapped ion approach. Now what is the story here, Peter? The story here is, what is an ion? Well, we take an atom and we either add an electron or remove an electron. Now we have a charged particle. We have an ion. And this ion now we can control, and several people, including Stephen Chu and many others, have won several Nobel Prizes over the last 30 years on technology that allows us to use lasers as tweezers to manipulate the state of an ion. That is, we can have the ion here or there, we can twist it, turn it, and we can turn the ion into a qubit.
Amazing.
And so this is one of the oldest ways, when I say old, I'm going back 40 years, okay? Oldest ways of building a quantum computer, and companies such as IonQ and others are now out there trying to build scaled quantum computers using the trapped ion approach. So the advantage here is that this is a well understood technology, and they're hoping to go beyond the 70, 80 qubits that they have today to thousands of qubits, and we'll talk about the numbers of qubits coming up in a few slides. But this is another approach. So in one approach, you have superconducting qubits. Here you have trapped ion qubits. And so these are two of the more popular ways that you have out there, both in academia and in industry.
And when we're talking about this, you're talking about actually have been physically built and actually
Physically
used
built,
to make measurements.
That's right. IBM, in fact, right now offers access to a very small, about 16 qubit computer on the cloud today. And what I expect to happen is that all the major cloud providers, Amazon, Google, IBM, Microsoft, all the major providers, and by the way, those in China as well, Alibaba, Baidu, and others, will be offering cloud-based quantum computing. And so this is going to democratize and distribute access to this very advanced technology. This is not like anything we've seen before, where typically, Peter, the rollout of major advanced technology typically happens at large companies or research labs or things like that. You need hundreds of millions of dollars. Nobody's going to buy one of these things. They're going to access it over the cloud in a hybridized fashion, putting part of the job on the classical side and then subroutining out the hardest part to the quantum computer, getting back the answer, and then continuing on with that calculation. Okay, so let's move on now. What we see here, this is really interesting. This was the first realization of Shor's algorithm. So again, to remind ourselves, Peter, from a previous module, we know that Peter Shor in 1994 put forth the mathematical proof that one day with a sufficiently powerful quantum computer, we were going to break RSA, break it with the kind of length of keys that we use today, be it 512, be it 1024, 2048, or so on and so forth. What Isaac Schwang did and his colleagues at MIT back in 1997, they put out a theory paper, and then in 2001, the demonstration of the experiment, they used Shor's algorithm on an actual quantum computing device to break and factorize a large number into its two prime numbers. Now, before you're super impressed, let me just tell you, what was the big number that they factored back in 1997 in theory, and then 2001? Are you ready?
I'm ready.
You're sitting down.
I'm sitting down.
Good. The number 15. Okay. They got it to 5
3 and 5.
Exactly. 3 and 5.
So when did we see the first quantum computer?
Well, this is actually one of the first ever quantum computers. So let's
2001.
remember that Seth Lloyd wrote that paper in 1993 that we referenced earlier, that we can possibly build one of these, and Isaac Schwang, his colleague at MIT, then set out to build one, and he actually used, we referred to earlier in our modules, NMR, nuclear magnetic resonance, or known in hospitals as MRI. That's what he's using. He's using essentially an MRI machine, not one that's a hospital-based one, but kind of an experimental one that we use in a lab. And he was able to then control the spins of subatomic particles to be spin up or spin down, and use the spin of a particle as a qubit.
Amazing.
So that's a third way. We talked about superconducting qubits. We talked about trapped ions. This is now a third method of trying to build a quantum computer, one that probably is not going to move forward. We don't think, most of us in the field today don't believe that NMR or MRI would be the way to move forward with a scaled quantum computer. And we'll see in a few minutes why that's so important. But it is important for historical reasons to note that this was the first implementation of Shor's algorithm. Yeah. But of course, we're now excited about going forward. So now let's talk about some of the applications of quantum computing. So a number of researchers, including Eddie Farhi and his colleagues, developed something called QAOA, and that basically is the O there is an optimization. And why is optimization important? Where do we use optimization, Peter, in industry today? Answer: everywhere. So if I had a telecom network, let's say you and I were running a very large global telephone network like Telefonica, Vodafone, Verizon, places like that, and we wanted to make sure that we had the optimal way to send our packets, our little data packets, these little data envelopes, that when I send you an email, my email gets sharded into thousands of little data packets and it goes over the internet. Well, if I want to optimize that voice traffic, data traffic, internet traffic, I may want to use a quantum computing device to understand the optimal flow of that data.
Sure.
Another example might be a very, very complex logistics network that has logistics.
Like LA traffic.
There you go. There you go. In fact, Volkswagen has engaged to use a quantum computer to figure out and model the traffic in cities as self-driving cars go from 0% to 5% to 10% and on as a percentage of the total number of cars on the road.
Yeah.
You can imagine, and we've talked about this before, that self-driving cars are going to dramatically change the patterns of traffic flow in a city. And so Volkswagen's doing that right now using quantum computing methods. Daimler is another example of an application of optimization and also now for material science. Well, batteries are a critical component of the EVs of today and the future. And one of the problems is that you want to optimize along the following three vectors. Weight, you want it to be as light as possible. You want it to have as long a range as possible, and the price to be as low as possible. And so now when you think about, Peter, all the material choices that you and I could make, if you and I were to design the battery of the future, we can make a choice for the electrolyte, for the membrane, for the anode, for the cathode, all these key components of the electric vehicle battery to then optimize for those three things.
Sure.
That's a very complex problem. Daimler is now using quantum computing methods to try to get at the optimal solution.
So when I think about quantum computing and I talk about the impact, it does, I mean, what I'm most excited about is material sciences, catalysts, and ultimately as well, pharmaceuticals. And I'm thinking about the notion that these are true physical systems. And using a quantum computer that is a true physical system as well to model it is, I mean, there's no, I mean, is it in fact that a quantum computer, because everything is quantum in its nature, in particular material sciences and pharmaceuticals and molecular interaction, is that why it's best?
Exactly right. That molecular-to-molecular interaction for drugs, for example, or even at the atomic level, we will have the tools on quantum computers, maybe not today, but over the next several years, to actually calculate that in a much more exact way. Because again, we're not approximating things on a classical computer. In the spirit of Richard Feynman, when he said, "Nature's not classical, damn it," we are now using quantum algorithms on a quantum device to understand quantum interactions at the molecular or subatomic level. So that is the key difference. And we can now think of so many applications. Let's talk about drug development as an example. Well, drug development right now, Peter, takes a long time. It takes 10 to 12 years for an average drug, start to finish, and billions of dollars. What if we can shorten that time? What if we can run through a number of the potential combinations? I'll give you another life sciences application that's happening right now. I was recently approached by a lab that said, we're looking at the metabolites in our blood of the breakdown of various proteins and other byproducts in the body. We recognize some of them by their spectra, so what they'll do is they'll take it out of the blood, they'll analyze it, and they'll look at the spectrum of that particular molecule. Now, they look up in a reference table, and they say, we know what that is. That's this particular molecule here. We understand that one, but some of them are not recognized because there's no reference table for them. With a quantum computer, in the near term, we should be able to run the actual equations that allow us to predict what the spectrum would be. As we know for hundreds of years now, every molecule, when we shine certain kinds of light on it, produce a unique spectrum. And those are the spectral lines that one can get.
So are you saying that we could actually theorize every possible molecule and create a spectrum for it?
Exactly. Create a reference table.
A lookup table.
Exactly.
Amazing.
And then when we analyze your blood, we take a blood sample and we run it through and we get the spectroscopy of what your blood sample is. We can now look at it against the reference table. So this is literally at the cutting edge of what might be possible right now with quantum computers. Maybe not today, but in the next few years.
And it's not just your blood, it's every toxin in our ecosystem.
That's right, that's right. This is just happens to be, say, from our bodies, but it could be anywhere. If you're taking a sample from water, of a river, of a lake, and you want to understand what some of the contaminants were in that particular sample, again, we may be able to create better lookup tables that with vast arrays of spectra that allow us then to compare it against the spectroscopy that we see from that sample. So that's another example of an application right there. Peter, I want to introduce our viewing audience to the term the NISQ era. We've had a number of acronyms across these different modules, and this is an acronym worth knowing because John Preskill, a well-known professor who focuses on quantum computing and quantum information sciences at Caltech, coined this term in January of 2018. And this term is NISQ. And what does NISQ mean? It means noisy, intermediate scale, quantum computing or quantum processing. Let's break that down. N for noisy. Noisy refers to that decoherence that we were referring to before. These processes that we're doing, superposition, entanglement, very, very delicate because again, any measurement, and when we say measurement, again, we don't mean that humans have to measure it. Just any photon, any electron, anything impinging on the system is a measurement.
Got it.
And so that's where the noisy comes in. Now, the fact is that our personal computers today, our mobile phones, our laptops, they also have noise. For example, if I take my laptop through a big magnetic field, right? Some noise might get into the system and some of the magnetic flux that's on the hard drive, that SSD, that solid state drive that's in my laptop, one of those ones might flip to a 0, or 0 might flip to a 1. So why don't our current laptops have all kinds of problems? Answer, error correction. Over the past 40 years, computer scientists have developed very robust error correction schemes, checksum schemes, other kinds of schemes that say, hey, wait a second, we did a calculation, I don't think it's right. And so there's a lot of error correction that's built into all of our computers today, which is why we get the right answers. But in the case of quantum computers, we're just at the beginning of understanding how to make error correction happen for these kind of computers. And so right now we're in this regime we call the noisy regime because we don't have robust error correction yet.
Got it.
I'm going to talk more about that in a second. Let's now go to the second part of this acronym, IS, intermediate scale. Intermediate scale means the period of time in which we're building and using quantum computers that have, say, 50, 100, 1,000, 2,000 qubits, but we're not yet at the millions of qubits that ultimately we'll need. So we call this the intermediate scale, and Q, of course, for quantums. Let's see what that looks like on the roadmap. Here's the critical roadmap, and this is the key takeaway slide of all the modules we discussed today, Peter.
All right, so let me build before we go
Yeah.
into this. We have been hearing over the last years qubits on the order of a dozen, 50, maybe 100. When you talk about millions of qubits, is that something which scientists, engineers, yourself, your colleagues believe we're going to hit at some period of time, or is that just theoretical?
It's a great question, yeah. So of the 8 approaches that I was referring to before, some of those 8 approaches include superconducting qubits, trapped ions, photonics is another approach that is being pursued by quite a number of interesting companies. All those we believe it's really just an engineering issue, not a law of physics issue, to get to millions of qubits. One of the approaches, the topological approach, a fascinating approach based on the work of 𝐂𝐄𝐒𝐄, really wonderful, interesting science, will need several physics breakthroughs to get us to millions of qubits. But it's still worth pursuing, by the way, because ultimately, if it does break through, it affords us potentially very resilient, robust, noise-resistant qubits. That the nature of those qubits themselves are quite noise resistant. So it's worth pursuing.
Sure.
But putting that one aside for the moment, we believe that we're now entering that blue zone that you see there. We're moving from the purple zone to the blue zone. This is the NISQ era that we just mentioned before, that John Preskill coined. We're in that 100 to a few thousand type of qubits. And there's certain things we can do there. Note the dot for quantum supremacy that demarcates the beginning of the NISQ era. And then what we want to do, Peter, is we want to land in the green zone. The green zone brings us to error-corrected quantum computing. Just like our classical computers today are error-corrected, but here's the thing. The basic ratio of getting physical qubits error-corrected to a certain number of logical qubits. By logical, I'm talking about fault-tolerant qubits that I can really depend on. Hey,
Sure.
hey, Mr. Qubit, I put you in a state 0. I know you're going to be in a state 0 after a certain time, right?
That's great.
Those kinds of fault tolerances, we have to wait for that ratio of 1,000 to 1. 1,000 physical qubits for 1 logical qubit. Now, with only 100 qubits, we only have 1,000 to make 1 fault-tolerant qubit. So therefore, we've got to wait to get to even a few thousand qubits to start making a handful of fault-tolerant, error-corrected qubits. So we are early days. We're in this blue NISQ zone.
What time zone are you talking about here? Is this a decade or?
Sure. Sure.
more.
You know, for each one of the technologies out there, it's probably a different time frame and timeline and roadmap. But let me say that a lot of us in the field believe that with all the venture capital, growth capital, resources being put at this, to give you some sense of that, I'm tracking personally about 75 different venture-backed investments. Not that I've made, but that I'm tracking in the field. About 75 well-known VCs backing different companies out there.
And that's not counting all of the defense.
Not counting governments, large companies that are putting millions into this area. So I think that we have the beginnings, Peter, of the ecosystem, of a speed up in the progress that we're going to make. Now, let's just give you a sense of it. To go from 22 qubits to 72 qubits, it may not sound like much, because that's what we've done, say, in the past 2 years. That's actually 50 Moore's law doublings. One thing we should mention right now to the viewer is that every qubit we add is a doubling of the power of the quantum computer.
That's amazing.
A doubling of the power. Let's recall back to the quantum supremacy conversation you and I had. 55 qubits bested 2.4 million cores of billions of bits.
Yeah.
Right? So when we talk about a qubit, these are beautiful, very, very precious things and very powerful things. So when we went from 22 to 72 qubits over the last 2 years, that was 50 Moore's law doublings. Now, I'll grant you we started at a low base, but normally Moore's law doublings happen every 18 months. Here we did 50 of them in just under 2 years. So I think we're in for a wonderful journey over the next 5 to 10 years. And I think in the next 5 or 10 years, we'll start to see the scaling up. Are we going to reach 1 million in all these 8 areas, all these 8 approaches? Maybe not. But you know what? We don't have to. I think what's exciting, Peter, right now about the journey is that we're having permutations across the landscape where, as a system, all of us as an ecosystem, we're exploring the total landscape of possibilities so that I think something very exciting is going to emerge. Can we say right now, is it going to be trapped ion? Is it going to be photonics? Is it going to be nitrogen vacancy? We don't know who will be the ultimate scaler in this particular platform race. But I think that several of them, at least 2 of them, will emerge as scaled up to 1 million to 10 million and give us the green zone, Peter, of where we need to go.
And that green zone with 1 million plus qubits unlocks what for us?
That unlocks all kinds of possibilities. For those interested in communications issues, it unlocks Shor's algorithm. Okay, that's when you can run Shor's algorithm on the kind of RSA length keys that are run today in government and industry and other places, and WhatsApp as it happens. But I think that's not really the big story. Big story.
I think about pharmaceuticals and material sciences as
exactly.
the biggest story.
That's the big story. The big story is material science, pharmaceutical, optimization of huge logistic systems. Think about the implications for the energy network and what we can do in terms of the energy infrastructure of the country or the world.
Can I take it just take pharmaceutical a step forward? When I think about the ability to use AI and quantum computing together. I think about the notion of an individual doing the development of a new drug and knowing that the drug at the end of their in silico experiment works. That without having to go through elaborate billion-dollar, decadal-long experimentation.
That's right. So again, we're years away from that, but what's exciting is we now have a pathway, we have a roadmap, we have proof in the pudding right now that we can build these devices, albeit very incipient, nascent devices today. So again, I want to also make sure that we demythologize some of the popular press out there that says quantum computers are here and they're cracking all codes today. There was a recent story just last week about that. On the one hand, Peter, we want to bring some of the hype and hot air out of the balloon, but at the same time, on a more fundamental basis, help our viewers understand the roadmap to a very, very promising and bright future in that green zone.
Amazing.
A green zone, Peter, that's going to give us insights, not just into these very practical applications. One of the key applications I want to leave us with is the ultimate goal of humanity. One of our goals is to understand ourselves, understand our place in the universe, and therefore understand our universe. And one of the most tantalizing possibilities of quantum computers, not of today, but in that green zone, is to do physics itself and probe the theoretical physics questions as to the nature of our universe itself. Today, we've made a lot of progress in physics over the last 100, 150 years, but All the stuff we know about matter and energy is only about 5% of the total universe. We know that dark matter and dark energy comprise the 95% of the rest of the universe, and we don't know what that stuff is.
Amazing.
So the question is, Peter, can we now use a quantum mechanical device in the spirit of Paul Benioff, in the spirit of Richard Feynman, the spirit of those visionaries who understood the possibility of this very powerful technology, to probe the very questions of the universe itself? That's also what excites us.
Jack, that's extraordinary. And what I want to just focus for you as you're watching this is it's going on right now. And these are tools that are not just for the largest governments, largest corporations. These are tools that are being democratized for entrepreneurs. And there'll be interface moments. There'll be classical, if you would, Netscape moments that allow people to use quantum computers to solve problems. And anyway, I just want to say thank you for the work that you're doing. And thank you so much,
Peter,
for
pleasure.
supporting us today on this. And I hope you guys have enjoyed this. Please remember, if this is your future, quantum computing and applied approach, it's sold out, but I'm sure it's being resupplied right now by Jack Hidary, a dear friend. Thank you, Jack.
Great to be here, Peter.
Take care, everybody.